Our speaker this evening was formerly an Air Force officer, a university professor of computer science, and spent 14 years on the SQL Server team at Microsoft. Please welcome the Principal Product Manager of MemSQL, Eric Hanson.
So it's great to be here today. I really like the enthusiasm on a warm, late spring day. And so today I'm gonna give you a spoiler right at the beginning, which is I'm gonna talk about processing a query in MemSQL at 1 trillion rows per second, and I'm gonna demonstrate it for you. So being able to process queries at that speed really opens up some new vistas for data architects, application developers, reporting analysts, anybody who's doing interesting and amazing things with data can really push the envelope with this kind of technology. So before I get into the details of how we're able to do this and actually demonstrate it for you, first I wanted to talk a little bit about MemSQL and just give you an overview of how the system works. I'll also say in this talk a little bit about interactivity and user satisfaction. So, how users react to really fast response time and how important that is for application software and data area. And I'll say a little bit about state-of-the-art query execution technology that we use in MemSQL to achieve this amazing 1 trillion rows per second results. And then I'm going to demonstrate it for you. And after that, we can talk a little bit about where we can go with this kind of technology, or given the performance that can be achieved, the high level of response time and concurrency that you can get with a technology like MemSQL. What can people do with that? So, first, what is MemSQL? Well, as Eric discussed earlier, it uses the SQL query language. So it's an SQL relational database management system. So SQL is a tried and true database languages that most of you probably know or have used at some point in your careers. And storing data in tables and using SQL to combine tables and extract information from the system. And an amazing thing about SQL database systems, the reason that they're so popular is that the SQL query language is a very compact and expressive language that allows you to extract data from the database independent of how it's stored. You don't have to care what kind of indexes are on the data or how it's physically stored, whether it's in memory or whether it's on disk, etc. SQL can allow you to get the answers you need without having to understand the physical structure of the data, which is really important. So it's really fast. We have a number of technologies that allow MemSQL to run queries at incredibly fast response time, very short periods of time to extract data from huge databases. One is scale out, where we gang together multiple computers in a cluster to do more work in the same amount of time than can be done on a single server. Another is compilation. So queries in MemSQL are compiled to machine code. So unlike traditional database systems like Oracle, like SQL Server, like MySQL, PostgreSQL, etc., all of those systems use an interpreted model where they take the query and they compile it to an intermediate code that they interpret that code. In MemSQL, we actually compile the queries to machine code, just like a C compiler or a C++ compiler does. And that allows some really great performance gains. Also, MemSQL has two storage structures. One is an in-memory row store. So the in-memory row store is fantastic for transactional type workloads. It allows us to look up rows at random from huge data tables, find them quickly, update them quickly, about a factor of 10 faster than you can do the same kind of operation on a traditional row-oriented database system like Oracle, like SQL Server, like PostgreSQL, etc. We also make extensive use of what's called vectorized query execution. So vectorized query execution is a technique that I'll talk a little bit more about later, where we process more than one row at a time. We process a vector of rows at a time, or we process, I should say, a block of rows at a time, and use vector-oriented processing to make that faster. So MemSQL, even though it's commonly misunderstood that all the data in MemSQL has to be stored in main memory. That's actually not true. MemSQL excels at using main memory for transactional type workloads and for fast ingest of data, but you don't have to have all of your data in main memory. MemSQL has a disk-based column store structure that allows you to store an arbitrarily large amount of data, much bigger than can fit in main memory. So the demonstration I'm going to give to you today is actually going to use the disk-based column store to achieve this incredible trillion rows per second result. And MemSQL, as I alluded to, can do both transactions and analytics on the same database, the same equipment at the same time. So this is a really big differentiating factor about MemSQL. Typically, if you wanted an application that was oriented around transactions, you picked one type of database. If you wanted one that was for analytics or data warehousing, data marts, etc., you might have picked another type of database. MemSQL is capable of handling both types of workloads on the same system and doing it really well. So that's a really important key differentiating thing about MemSQL. Now, MemSQL can do transaction management, it can do analytical processing, data warehouses, data marts. One place, however, where MemSQL really shines is as what some people call an operational data store. So it's a system where you're ingesting data really fast from a transaction processing system into another system which you use for analytics. MemSQL can ingest data so fast and handle really fast high-performance updates on that data that you just read, and then do analytical query processing. It does lots of joins, group by, aggregation, and so forth on that data under heavy concurrency, and do that really well. So a lot of people have had great success using MemSQL this way to replicate data from the transaction processing straight into MemSQL for instant analysis at any scale. So, to summarize why you might want to consider using MemSQL, there are 3 key points about it. One is fast data ingest. So MemSQL is amazing at ingesting data or loading data very fast from operational sources or from files, whatever sources you may have. It can suck in a phenomenal rate of data. So millions of rows per second inserted or loaded into MemSQL is commonplace among our larger customers. It also supports very low latency query processing, both for transactional type queries, looking up just one or a few rows, or more complex analytical queries. Both can be done in a fraction of a second. So MemSQL, it's a database management system, so it has a query optimizer, it has a plan cache, and when you submit a query that's already been run once, you grab the query plan for it out of the cache and run it very, very fast. It's already compiled, it's already warm, all the data structures are all in memory, so in less than 100th of a second, you can look up a plan from a plan cache and execute a small query. And for larger queries, they can still, you'll see, they can still be running in hundreds of a second. MemSQL is also really good at handling high concurrency. So if you have a very large number of concurrent queries, multiple users running queries at the same time, MemSQL can handle high concurrency. And it's very good at allowing you to update data and query it at the same time. So some users can be updating, some can be querying at the same time. Readers and writers don't block each other. So as I mentioned earlier, MemSQL is a little different than traditional database systems like SQL Server and Oracle don't have a true scale-out architecture. MemSQL does. So what is a true scale-out architecture? It's an architecture where data is divided across multiple nodes in the system evenly, typically using some sort of hash function. So if you look at, okay, you can see here in MemSQL, at the bottom we have what are called leaf nodes. So when you create a table in MemSQL, it gets split evenly across the leaf nodes using what's called hash partitioning. So you pick a key, which is one or more columns of the table, and that's used to determine which leaf node contains the row with that key. The aggregator is a front-end node where your client application connects. The client sends an SQL statement to the aggregator, it compiles it, it caches the plan, and then it starts running the plan. So it'll send commands out to the leaf nodes telling them to start portions of the query running. The leaf nodes may talk among themselves to distribute data. When they're done, they send back intermediate results to the aggregator, which formulates the final result and sends it back to the client. So traditional database systems like MySQL, like PostgreSQL, like SQL Server, don't have this scale-out technology. So some of the data warehouse databases out in the market and big data systems do, but there's no other system in the market that can do analytics and transactions that has scale-out. That's competitive in the market today besides MemSQL. So Oracle has some scale-out capability with their Exadata system, but only at the data layer, the scan layer. They can't do scale-out for joins, for example. MemSQL has complete horizontal partitioning and allows us to do very high query performance for all the different operators in your query plan. So to get really fast interactive query response time, especially for analytical queries, there are a number of challenges. So one of these challenges is handling large data volume. So the scale out, the column store technology that we have in MemSQL can handle that data volume, can handle arbitrarily large data volumes. Lots of concurrent users is also a challenge. We support multi-version concurrency control, which allows us to have readers and writers running simultaneously and they never block each other. It's very helpful for high concurrency. Also, very complex queries are an issue. So, MemSQL supports a query optimizer and very sophisticated query execution that can handle very complex SQL statements. Also, rapidly changing data is an issue. And I talked about the in-memory row store that we have in MemSQL that can allow you to ingest data extremely fast. And also, column stores have an in-memory row store buffer that sits in front of them that allows very fast ingest of data to the column stores as well. All right, so I talked about MemSQL, what it's good for, some of the things that make it different. Now, shifting gears a little bit, I want to talk about the interactive response time and productivity and user satisfaction. So before I get into some discussion about interactive response time, what it is, how it impacts user psychology, I want to just tell you a little bit of a story, a personal story. This is not scientific. This is not meant to be the general extrapolation of what has happened in the industry in the last 12 years. It's my story experiencing interactive response time. So, or not interactive response time, as the case may be. But let's go back to 2006. So I was using database X, let's call it SQL Server, and loaded up 100 million rows on a small server. At this time, I was actually responsible for data warehouse and data mart type features for feature planning for SQL Server. And I was pretty disappointed because on a small server, it took me 2 minutes to query 100 million rows from beginning to end, just to do a scan query that did a grouping and aggregation, produce a small summarized result that actually looked at all 100 million rows. 2 minutes is a long time. You know, it's very tedious to sit there for 2 minutes. People want interactivity. This is not a satisfying experience. All right, fast forward 6 years. 2012. So SQL Server had introduced column store technology, which I had been a big part of introducing that column technology in SQL Server. We loaded into a larger server than I used in 2006, but it's still a single processor with, I don't know, maybe 8 cores, 16 cores, loaded 1 billion rows, and we're able to process it all in about 2 seconds. So 1 billion rows is a substantial amount of data. 2 seconds is almost instantaneous. You can't perceive a delay, but it's pretty quick. Huge, but look at the improvement from one generation to the next. It was like 3 orders of magnitude plus in 6 years. So the 1 billion rows is a substantial amount of data, but it's not near as much data as a lot of people have in their big data sets, their transaction processing data sets for large, Fortune 100 type enterprises. Even smaller companies that have a lot of event data, like advertising technology and financial companies. So 1 billion rows, while it's a lot, people have a lot more data than that now. So fast forward to 2018, using MemSQL, I was able to process on a reasonable sized MemSQL cluster, which I'll talk about later in my demonstration, 58 billion rows of data in 0.05 of a second. So again, we're talking another 3 to 4 orders of magnitude improvement. This is my personal experience over that 6-year span, that second 6-year span. So we've gone from taking minutes to process a moderate amount of data to a few seconds for a substantial amount of data to a tiny fraction of a second for a gargantuan amount of data. So it's a major transition in technology and really sort of allow database architects and database application developers, big data developers, application software developers of all kinds to really kind of think about how they can push the envelope and make the user experience great for really large data sets. All right, let's talk about what it means to have interactive response time. Maybe it's time to get a little philosophical before that. As I was reading about the user psychology of interactive response time, I came across an interesting quote by William James from a psychology textbook written in 1890, a very long time ago. Stimulation is the indispensable requisite for pleasure in an experience, and the feeling of bare time is the least stimulating experience we can have. All right, so what does that mean? What is he really trying to say there? Really, it's just a very beautiful way of saying that people hate to wait. Waiting with no outside stimulation of any kind is extremely boring and tedious. People hate it. So, users are very sensitive to the speed at which computer systems provide results. For example, you've had this experience yourself. If you use a computer system and it produces really fast results, you get used to it very quickly. And if it doesn't perform the same way in the future, you get very frustrated. That spinning circle, it spins for 1 second and then comes back, and then the next day it spins for 20 seconds. You're about ready to put your fist through the terminal, right? So users get used to it and they expect it. Also, surprise, surprise, user satisfaction increases as response time decreases. And in fact, there's no lower bound until you get down to about 50 milliseconds, at which time the human mind perceives it as completely instantaneous. So if response time continues to get better, satisfaction will increase all the way down to that level. Also, delays of over 50 to 150 milliseconds are noticeable in real-time applications. And these are apps like video games or text editors. Like if you press a key on a text editor and it takes more than 50 milliseconds for the character to show up on the screen, you will notice it, and you will not be happy with that. So these are real-time apps. That's sort of pushing the envelope for where response time matters, but people can actually perceive this stuff. Also, 250 milliseconds is the median human reaction time. Now, that means if someone, takes a swing at you, it'll take like a quarter of a second before you realize it and step out of the way so you don't get hit or something like that. Actually, the most elite humans, people like Stephen Curry, and great baseball players, fighter jet pilots, and champion video gamers, their response time is about half of that. That's the limit of human performance. Okay, so I said people get used to fast response time, and they expect it. That's true. Although there are some subtleties about response time that are not obvious. One is that high variance in response time can bother users. And that's not just on the slower side, it's on the faster side as well. So if the response time is less than 1/4 of the mean, or more than twice the mean, users tend to become dissatisfied. So it can help if you give messages in your applications if you know the response time is going to be out of these tolerances. That can help users be a little less frustrated or surprised. Now, weirdly enough, unexpectedly fast results can make users apprehensive. So, we've actually seen this with MemSQL where they were running a query on another database product, and they installed MemSQL, installed the same data set, ran the same query, and instead of taking like 2 minutes, the query took like a second. And they're like, whoa, there's something wrong here with the system. That can't be right. You must have pre-calculated the result or something. So it actually can make users a little apprehensive. However, they quickly get used to it, so it's not a big problem. But it's something that you might experience. Now, fast response time also changes the way users interact with a computer system. It can lead to more, unintuitively, it can also lead to more input errors. What does that mean? It means that they filled out a form wrong on the screen and pressed the go button. That could be an input error, and they got an error message and they had to start over. So having more input errors, so you can imagine why this is. Why do you think that might be? Well, it's because they know that if they make a mistake, they can recover from it very quickly because they just try again. Now, if it takes a minute to get an answer, and you have to fill out a form, and it takes a minute, you're going to be very careful to check your input before you press the go button. So, but fast interactive response time, although it might prompt more user input errors, it's better because it makes users interact and explore the data more, explore the computer system more, and especially in a data analytics system built on a database, that creates business value. Having the users run more queries, more reports, explore the data more is going to allow them to make business decisions that typically will far outweigh the cost of the information technology. In this case, maybe a cluster of servers and MemSQL software. The benefit that they may get could be much greater than the cost of the technology. So I wanted to move on and talk a little bit about MemSQL query execution technology. 1 second. Okay, so I'm going to demonstrate for you a trillion rows per second query execution. So the question is, how does MemSQL do that? MemSQL gives lightning fast query response time for analytical query processing using these technologies. One is scale out, which I already discussed. The other is compile queries. I also discussed that, where we compile queries to machine code like a C compiler does. And we use an in-memory row store technology. Other database systems that use row store technology, they're typically disk-based, and then so the row formats are designed for disk and not for in-memory. So it takes more time to process the rows in that format than it does if it's in a memory-specific format. Column store also helps us process queries faster, and I'll talk a little about how column store works. Also today, we do use what's called vectorized query execution, and that helps reduce response time as well. And finally, we use single instruction, multiple data instructions on Intel processors using what's called the AVX2 instruction set, which is available on pretty much all Intel processors built in the last 3 years. I'm just curious, how many of you heard of SIMD before? Okay. Maybe a quarter. Okay, we'll say a few words about how that works, what that means. So, as I said, MemSQL compiles queries to machine code, and let's just look at, kind of what impact that has. So, databases like Oracle with a row store, like MemSQL, SQL Server, not MemSQL, MySQL, PostgreSQL. Those databases have a disk-based row store structure, and you can process about 1 to 2 million rows per second per core, per CPU core on those systems. This is an example, a real example from MemSQL, just running on my Mac, which just has 2 cores. And this just tells you how big the table is. It's 8 million records. And so here's a non-trivial query. I mean, it's pretty simple, but it's not. It's actually doing a filter. It's looking at every row. So it's counting the rows from T where the color column is red. And so half the rows have red. And so this includes compile time. It's actually generating code to run that query and then running it. Here we run it again, and it takes less time. See, it takes 0.17 seconds on 2 cores to scan a little over 8 million rows. So doing the math, that's 49.3 million rows per second. That's 24.7 rows per second. 24.7 million, there's a missing million. 24.7 million rows per second per core. So that's more than an order of magnitude faster than a typical database management system product. So that's just one place where we get a lot of performance benefits in MemSQL. By compiling queries to machine code for our in-memory row store. Now, MemSQL also has a column store structure. And the way this thing works is we store data on disk. The data is broken into 1 million row chunks. They're called segments. So these things here, those are segments. See those? 3 different segments. Each column within a segment is stored in a separate file on disk. And those files are cached in the main memory buffer manager by the operating system, by the Linux operating system. And you only read the columns you touch. So if your query only scans, if you're only filtering, say, on one column and doing a count, maybe you're filtering on the 3rd column, you only have to read the 3rd column from disk. The other ones you don't even have to read from disk and spend any time on. So that helps with performance of the column stores. And column stores compress the data very highly, and that helps reduce query response time by reducing how much data you have to read from disk or read from memory into the processor cache. And then the minimum and maximum values of each column are stored in metadata for each segment. So if you have a filter, for example, you could skip an entire million row chunk segment. If your filter says, you can look at the minimum and maximum value metadata for a column, and there's a filter on that column, you might be able to skip the whole segment because you know nothing in there is going to qualify. So the next technology that we use in MemSQL to get fantastic interactive response time is called vectorization, also known as vectorized query execution. So MemSQL would process data in 4,000 row chunks. And our internal terminology for that is called a vector projection. Other implementations have used different terminology for that, but that's what we call it. And the basic idea is that when you fetch data from a scan, you fetch a 4,000 row chunk of rows instead of a single row. So the fetch next operation, you amortize it by processing a lot of rows at once. And then once you got that block of 4,000 rows, each column within it is stored in an array or vector of primitive data type. Like in this case, it's a 64-bit word of data. And so processing, say, a filter against a 4K row chunk, you get the 4K row chunk, that takes some time. Then you grab the column vector for that column, and in a very tight loop of C or C++ code, you zip through all 4,000 values. You don't have any function calls or anything, so it's very low overhead per row. So this is very, any state-of-the-art analytical query processing system needs vectorized query execution, or it's not competitive. So MemSQL uses vectorized query execution extensively. Using just vectorized query execution, you can process a scan at a few hundred rows per second per core, like maybe 200 rows per second per core, 200 million rows per second per core, or so. All right, so remember earlier I asked about SIMD or SIMD. So SIMD is another technology we use in MemSQL to get very high performance query execution, and it is what we call a low-level parallelism technique that is provided by the modern Intel processors. And so the Intel chips have a set of 256-bit registers. So a regular word that fits in a register on a computer processor has how many bits these days? 64, right? So 256-bit registers can hold 4 words of data. And so each of these represents an integer that's packed into a 64-bit word in a larger 256-bit register. And so this is an example of a simple addition operation using SIMD or SIMD on a word-wise basis where the words are 64-bit units. And so we have a 1, 2, 3, 4 stored in 4 different slots in a SIMD register, and then 1, 1, 1. 1 down here, and we add them together pairwise. So 1 plus 1 is 2, 2 plus 1 is 3, and so on. So we pairwise add together the 64-bit components of a larger 256-bit register, and we get the totals, the pairwise totals. There's 4 totals in the output register. So the modern Intel chips have a whole bunch of instructions for operating on these 256-bit registers, including all the arithmetic instructions, add, subtract, multiply, divide, modulo, etc., logic and or not, loading, storing, etc. They even have some neat instructions for loading and storing, and they're called scatter gather, where you can load 4 values from 4 different places in memory in a single instruction cycle. So anyway, the neat thing about SIMD is it allows multiple operations in one instruction. And it doesn't have to be just on 64 bits. You could do it byte-wise. There are some instructions that operate on bytes, on 8 bits, some on 16-bit chunks, 32-bit, or 64-bit chunks. And so, you could even do 64 single byte AND operations. I guess 32 single byte ANDs in a single clock cycle in a single instruction. So this. I'm sure you're all pretty much familiar with the idea of multiple cores on a CPU. And each core can run a single thread of control. But within each core, normally you're just processing one piece of data at a time in a single register. This allows each core now, while it's executing an instruction, to operate on up to 4 64-bit words at a time, or even 8 or 16 or 32 units of smaller size data. So it's yet another piece of parallelism that can be employed in query processing. We've got parallelism through scale out, we've got parallelism through multi-threading on each server, and we've got parallelism down at the SIMD level within each instruction. And so, MemSQL makes use of SIMD to do what's called operations on encoded data. So we use Intel ADX2 SIMD. We can do filters on encoded data. I'll tell you what encoded data is in just a sec. We can do group by really fast. We can process 256-bit chunks of encoded data, and we can process more than 3 billion rows per second per core this way, and it's done before the vectorization stage, which uses those vector projections that I showed. So here's an illustration of what is encoded data. So column stores store data compressed, and a common type of compression is called dictionary compression. So suppose you've got a column with a table. It has 3 values, green, red, and blue, and they're stored as character strings. It could be like a varchar 30 column, but maybe you just so happen to only have 3 unique values in that column, green, red, and blue. You can store what's called a dictionary, which is all the unique values in that column, and for each dictionary entry, you've got an ID number, which is 0, 1, 2 in this case. So that's the binary format. So with only 2 bits, you can represent each of those 3 colors. And so when you compress the data in that column, you can use dictionary compression and pack it together in memory on disk in those column segments I talked about, so that each one is packed together right next to each other. And so in 256 bits, you could have 128 values from 128 different rows packed in a single register. So this is an example where you pack 6 values from 6 rows in only 12 bits. So a query like this, like select color, count star from T, group by color, MemSQL can process a query like that by applying SIMD operations directly on these encoded data values that are stored just the way they're stored on disk and brought directly into memory. And you can process multiple values in a single machine instruction to handle more than 1 row per instruction in some cases. Okay, so I'm about to do the demo, and before I do that, I want to thank our hardware partners, Intel. So Intel has generously provided access to us to a cluster consisting of 9 servers. I'll say more about that later, but they're using state-of-the-art Intel Skylake chips that just shipped last fall. These are the highest performing Intel chips available for servers. While they're high-end processors, make no mistake, this is still general purpose equipment. It's not terribly expensive. It's not like a special purpose database machine. This is industry standard hardware that we're using with very high performance, the high end of it. So the hardware that we're using for this demo is a cluster consisting of 9 total machines, 8 leaf nodes, right here, these are the leaf nodes, and an aggregator node. And so I'm going to connect to the aggregator and run a query. Each leaf node has 2 processors. There are these Intel Xeon Platinum 8180s. They have 28 cores each. So each leaf node has 56 CPU cores and has 112 hardware threads maximum. I'm actually going to only use 1 thread per core for this demo. So 56 cores per leaf, total of 448 cores on the leaves, and that's what's going to dominate the runtime. The aggregator is actually the same as the leaves, although it probably didn't really need that much hardware on the aggregator to do this demo, but that's the way it's set up. So does anybody have any questions about this equipment right now?
So having like a higher thread per core, you actually even more or not?
So the question is, if I use more threads per core, could I increase the performance more? I think I could have increased it a little bit, but it wouldn't double. I didn't actually test it both ways on this particular configuration, but you can get more performance by using hyper-threading with MemSQL. So, all right. Another question about the equipment back there?
Where's the equipment?
Where is the equipment located? Okay, this demo that I'm going to do is running in Phoenix, Arizona right now. We're connecting to Intel's data center that they use for testing in Phoenix. One more question? Yeah.
So what I'm trying to understand, each leaf is like a separate node?
Yes.
It's a separate node.
Yep. So yes. So each of these is a server. Okay. And we actually installed MemSQL by putting 2 MemSQL processes on each leaf server. We have a terminology of a leaf in MemSQL. So yeah, we have 2 MemSQL software leafs running on each leaf server. We have 1 per chip. And so we've enabled NUMA awareness on this to get better performance. This network, I think it's a 10 gigabit Ethernet. Okay. All right, the data that I used for this demo is synthetically generated stock trade data. So I generated 56 billion rows of synthetic data, which represents stock trades on the NASDAQ stock exchange. It's not real data, but it's fairly realistic, and that it is skewed to the higher capitalization stocks have a lot more trades. And so I put, as I said, 57.8 billion rows of data in one table. I'm going to process it. I'm not going to scan 1 trillion rows. I'm going to scan it at a rate of more than 1 trillion rows per second. So, when you drive 100 miles an hour, you don't drive for an hour or 30 miles an hour. 100 for 100 miles, right? You might just do 1 lap of the track. So that's kind of what I'm going to do here. 57.8 billion rows is a lot of data. So how big is 1 trillion? Since I'm going to talk about scanning 1 trillion rows per second. It's the dollar amount of a football field covered with stacks of $100 bills 6 feet high. It's the number of tweets in 5 years. It's the number of text messages sent in the entire world in about 45 days. Every country in the world. It's more than the number of checkout transactions at Walmart since it was founded. So it is a very phenomenal number. All right, so let's take a look at this. Totally spoiled it by telling you what I'm going to do, but anyway, let's take a look, see if we can actually do this. All right. Okay, just to prove to you how much data I've got in here. Oops, got a better query here. All right, so I'm going to count the number of rows in the table. So I use that format function because there's so many digits there. I can't read it without the format function of a commas between the digits. But that's 57.7 billion rows. So now that particular query, we do have technology in MemSQL that knows how many rows there are in each million row segment. So it's not really looking at every single row. That one is kind of cheating. All right, see, it takes 0 seconds to run that. All right, it's not really looking at every single row. All right, let's take a look at see this query here at the bottom. It says, so it's doing a group by on stock symbol and a count star. And then it's got order by the count, limit is in descending order, limit 10. So what does that say? It says, tell me the top 10 most traded stocks of all time. Okay. So, let's run this. Boom. Look at that. 5/100ths of a second. Okay, and as you can see, the larger capitalization stocks are represented here because it's skewed. There's more trades for the larger cap stocks like Amazon, Cisco, etc. So, how about that? 5/100ths of a second.
That's awesome.
Okay. Yeah. All right. You just saw a trillion rows per second query. And moreover, we actually did spend time on every single row. Okay, this is not cheating. We did not cache the answer. The data is compressed very tightly using dictionary compression, and we're spending very little time on each row. but it actually is spending at least a little bit of time on every row. We're actually handling multiple rows in parallel with that SIMD or SIMD technology. So, yes, question.
What's the cardinality of the stocks and how many stocks?
About the question was how many unique stock symbols are there? About 3,000, a little over 3,000. So now I want to get a few more significant figures, and so I can calculate the scan rate with some more digits. This is only one significant figure right here. So I wrote a stored procedure to run this query in a loop, and I'm calling it and running it 100 times in a loop, and we'll see how long that takes. And we divide by 100 to get a little more accurate, high resolution amount of time to run the query. So it's going to be 0.0529 seconds to run the query.
It's running the same query 100 times. Is it just pulling the cache result 99 times?
So the question was, it's running the same query 100 times. Isn't it just pulling the cache result 99 times? So it's not, the data for that query is in the file system buffer cache. That the stock symbol column segments from the column store, that's in memory, but we have to process every single row anyway. So it's not caching the result, it is caching the data for that column in memory, but it has to calculate the grouping by looking at every single row. So it's not caching the results. So here's a query that calculates the actual rows per second scan rate. So it's count divided by the rate. So it's 1.091 trillion rows per second. All right, it's not 1 trillion rows per second. Okay, thank you. Thank you. Question?
One question on that. I thought it said 5.29 seconds, and then you did 0.005.
Well, because I ran the query, the question is, it said 5.2 seconds, not 29 seconds, and I used 0.05. So what did I do? So I just divided by 100. Yeah, because I ran it 100 times in a loop just to get more significant figures. Yeah.
Very good question.
Question?
So what's the impact of running that same query on more columns?
So what's the impact of running that same query on more columns? So it would take long, queries like that on multiple columns that are more complex could take 10 to 100 times longer. But there's, on a single table, but they're still going to be pretty amazingly fast. But then this is a best case scenario. Yeah.
How about cardinality? That's why I asked.
Okay, cardinality. So the question is, what if you have a column like the stock symbol column, you've got higher cardinality with this, so is it still going to be this fast? Once you get up to around 10,000 or so cardinality, we ship algorithms to use different approaches to do group by, so it will slow down. So we're taking advantage of the fact that the data's got low cardinality, but lots of reports do have low cardinality in the group by column, so it's still realistic. Yes?
And how much memory each node has?
So how much memory does each node have? Each node has 384 gigabytes of RAM. It doesn't really matter in this case because the column takes, that compressed stock symbol column takes a lot less than that. So it's just, it's CPU bound. We're not doing any I/O. But yes, these systems do have 384 gigs per leaf. Yes?
Is vectorization and those term you use to describe why it runs much faster just another way of saying feature map, or what is the secret behind it?
Okay. So the question is, what is the secret behind vectorization and why is it faster? That's more or less what the question is. Really, it just, there's two parts to it. The basic vectorization that I showed with the vector projections, that basically makes things faster by amortizing the cost of calling fetch next on a scan operator, which takes a few hundred instructions. and then when we're processing each cell within the vector, it only takes like 1 or 2 instructions. So it's just amortizing something that's expensive, and then in the inner loop, you're doing something very quick on a per row basis. And then we sort of continue that same theme by adding SIMD to it, where we're in the inner loop, we're not doing function calls, we're using very few instructions, we're trying to be cache friendly, so most of the data is in the CPU cache that we're operating on. Yeah. Questions?
In your demo, you're using an extraordinarily large single table, am I correct?
Yes.
Which is not really good design.
Right, okay.
And so in the real world, one would hope that this would probably be some kind of join or whatever.
Right.
How would that affect?
Okay, so the question is, she observed that this is a single table query. Typical real applications use joins and don't keep everything in one table. You're absolutely right. So this is the best case scenario for group by aggregate queries, and this is in MemSQL 6.0. MemSQL also has very high performance join technology. We're continuing to push the envelope on how we do joins in MemSQL. So we haven't shipped it yet, but we're working on this sort of in-memory SIMD technology for star join type queries. That you can expect that in MemSQL's future. I'm not going to give you an exact date. The join technology that we currently have is still darn good, because we use compilation, we scale out. It's still very good, but it's a couple orders of magnitude slower than something like this to do a star join. Question?
What if you had executed that on something that's like more horizontally scaled, as let's say 500 leaf nodes with 1 core each?
Yeah.
What would the difference have been?
So the question is, what if I use 500 leaf nodes with 1 core each, like 500 servers, 1 core or small servers? It probably would, it might slow down due to the communication between the nodes, but it also might speed up because these smaller servers have more like, if you just have 1 or 2 cores, you get better use of cache and more cache per core, typically. So it's hard to say what would happen. It probably would slow down just because of distributed computing complexity of more messages, but it might be faster. You'd have to try it. Yes?
Without caching, how much difference between that? Without caching means if you cross the cache, and without caching, if you execute the query, then how much time it takes? And with the caching, how much difference it comes there? What is the variation?
The question is, how much time does that query take if the data is not cached in memory first? I don't know the exact amount of time. All I can tell you is that if I restart those servers, it still takes less than a second. So it takes a lot more. It takes at least 10x slower than that 500ths of a second when you're reading it from disk. I'm going to take 2 more questions and then I'm going to move on. I'll stay around afterwards. We have a long Q&A afterwards. Yes?
Can this run on AMD processor?
So the question is, can it run on AMD processors? The latest generation of AMD processors does support AVX2, so yes. Yes?
In real life situation, companies or individuals usually don't have the access to 384 gigabyte servers.
Yeah.
They have too much less. And in normal situation in big data, the data set actually bigger than the amount of operating memory on your cluster that you have. What do you do in this case?
So, you're saying what happens if the data doesn't fit in memory? That's basically what the question is. So, interestingly enough, with very high performance I/O devices, a lot of queries where the data doesn't fit in memory, if they're using, say, very high performance SSD drives, a good I/O system, the query execution time is still CPU bound. So at some point, you may become I/O bound. At that point, then yes, you're right, the I/O will dominate.
Right, but you still have to write or read from the disk in that case. If you don't have enough operating memory, you can't load the whole data set in memory. You need to do the swapping, you need to do shuttling, and tons of other things that big data systems deal with. looks like you kind of, pushed it aside.
MemSQL uses for the column store, we use the file system buffer cache to do our in-memory caching. So the file system buffer cache is going to use an LRU-like algorithm to decide which portions of the table to keep in memory, and we can handle data that's much bigger than memory. Okay, so that's it for questions for now, and we'll take Q&A afterwards. I'll stick around for a good long time afterwards. Okay, so what does it mean now that we can get interactive response time at this level? You can encourage analytic exploration of the data. So I think that's the biggest thing. People don't like to wait, but if you can have interactive response time on complex analytical SQL queries, people are just going to run a lot more queries, a lot more reports, and learn a lot more from their data, and make better business decisions, and ultimately get value from the data. And so the technology exists to meet all these challenges. One is that users expect interactive response time. Another is that the data is growing at a tremendous rate. People are demanding higher concurrency, so there are many organizations that have hundreds of users that want to be able to query the data at the same time. And if you've got hundreds of users hammering on a system like this at the same time, they're not going to get 500ths of a second response time, but you could get sub-second response time for dozens or maybe even hundreds of users in a situation like that. Real-time update, well, I should say that people have a preference for SQL. There's a reason that most of the revenue in the database market is going to SQL relational database vendors. There's something really beautiful and important about SQL. It's a non-procedural language and a very compact statement. You can say what you want and not how to get it and get it back from the database. So we leverage that important piece of technology in the database industry, SQL. And real-time update is also something that you can combine with analytics. So we could be inserting data into that table and querying it simultaneously and still get that super interactive response time. Finally, people want and need to run on economical hardware. They want to use industry standard hardware, not some special purpose database machine. And application architects and data architects, database developers they need to be able to run their applications wherever they need to, whether it be in their data center or in their favorite public cloud platform. Be it AWS, Azure, Google Cloud, or any other public cloud provider. So just think, what could you do if you could get that kind of interactive response time on your largest data sets? How would that impact your users? How would that make you look as the person who built that application? So if you want to try MemSQL, just go to memsql.com/download, and you can download our MemSQL 6.0 or our new MemSQL 6.5 beta version, which is the general release version of that is going to be shipping pretty soon. It's just a matter of a few weeks, most likely. If you want to learn more, you can get a personalized demo. You can go to memsql.com/demo. If you have questions about pricing or the product, talk to the team at memsql.com by email. And again, you can go to memsql.com/download to download MemSQL and try it. And I want to emphasize that there's an event coming up shortly on June 6th, Wednesday, in Manhattan at the Maxwell Hotel in Lexington. There's two events happening the same day. One is for media and advertising technology companies, or media and advertising companies in general, technology or not. That's from 8:30 to 10:30 a.m. This is the breakfast roundtable discussion. And from 2:30 to 5:30, there's a finance session. There's multiple sub-sessions within this time block. The first is about digital transformation in finance. And then there's some demos and a customer case study by one of our customers, Novus. And there'll be a networking happy hour afterwards. So I think that you'll find that very entertaining and informative. And if you want to learn more, you can go to memsql.com/nycmedia or memsql.com/nycfinance. It's open to anybody who wants to come, who's in the industry or has other interests in it, but you need to RSVP beforehand. So please mark your calendar for June 6th. All right, thank you very much. And I'll stick around after this.
Thank you, Eric Hanson. He will be here for one-on-one questions after the QA, but let's take a few more. We have time for only a few, though. Who wants the next question? Yes.
So this is a little bit tricky. So all the SQLs are basically SQL machines, or you have design first and data load, everything is later. But can MemSQL also behave like the NoSQL products?
Okay, so the question is, can MemSQL behave like the NoSQL products? And so we're SQL first, we're oriented towards structured data, but we do have the capability to handle unstructured or semi-structured data. We have a JSON column type, so you can use, put your structured data however you want it in tables, but if you have something that's really unstructured or semi-structured, you just use a JSON column and you can add new elements to that. Did you have a question?
Applications in media advertising. I thought your example was great. If you're going to be analyzing the entire stock exchange for the last 20 years for a trillion line two. What do you think the applications are if you're talking about more structured data in an area that's not always very structured, such as media types?
Okay, so the question is, what are some of the applications in the media area? We have several customers that are using MemSQL in media. For example, we've got Disney, ESPN. So they've got multiple web apps where people can consume media. They can browse videos, watch videos. And they're interspersed with advertisements, and they can touch the ads and that kind of thing. So all the event data that Disney gets through those apps is recorded in MemSQL tables. And so I think they use a combination. I don't know exactly. I'm pretty sure they use a combination of our structured data and JSON types. And they have very large data sets.
Thank you.
Yeah.
Right here. You.
Yes.
You compare MemSQL only with traditional SQL database, but what about comparison with HANA?
Okay. So I compared MemSQL with traditional databases, and you asked about what about comparison with HANA. So SAP HANA does have some similarities to MemSQL. It stores data in memory. It has column store. It has vectorized query execution. So there's a lot in common. I think MemSQL, you'll find that it, in terms of ease of setup and deployment on general purpose hardware, there's some differences there. Also, I don't know how they would do on this particular query. They do use SIMD in their implementation, but so MemSQL, in that we do have column store and row store. It's a general purpose system with stored procedures. So it's a good question, and I'm not sure how they would stack up against this particular demonstration.
The gentleman in the blue shirt.
Yeah. I got a question about the compiled SQL. Can you put that into like a CX SQL, and does it, how does it play with the C, like a C client?
Okay, so I think the question is, can you write an application that's written in C and use MemSQL? Is that the question?
Well, I mean, in the sense that you can compile the SQL right into machine code. Can you link that?
Okay, so we do compile SQL queries to machine code,
Right.
but you can't link the query itself directly into a C program. If you want a C program to be able to access MemSQL, you can just use ODBC or some other client API to communicate. You can't extend MemSQL with your own C code. Yeah.
That is all the time we have for tonight, but Eric is here for one-on-one questions. Thank you all for coming. Thank you, Eric Hanson.